Swayam Prabha. Digital India. Educated India.
So, welcome back. Today we will do a couple of examples, tutorial examples on open circuit and short circuit test, and after that we will proceed with some basic theory of auto transformers, a beautiful device that it is. So let us start with a with this problem here. The following test results were obtained on a 50 kVA. Following test results were obtained on a 50 kVA transformer. The primary voltage is 3300 volts, secondary voltage is 400 volts, primary power is 400 watts. So, let me just write it down here. This is my V1, this is my V2, and this is the open circuit test losses. You know that the open circuit test losses basically cover the magnetic or the core losses, the hysteresis and the eddy current losses. And since they are obtained at the rated value, so therefore, this is more or less constant throughout the working phase or operational phase of the transformer, because supply voltage is usually kept within plus minus 5% of the rated voltage. Now, short circuit test, the primary applied voltage is 125 volts. Again recall that we apply this much lower fraction, it is 125 by 3300 per unit, or 125 by 33 125 by 3300 into 100, which is 125 by 33, which is around so this is percentage, and this is in percentage 125 by 33. This much small percentage of this much small percentage of voltage, some 3-4% of the actual applied voltage, because 33 3s are 99 and 33 4s are 132. So, it is somewhere close to 4% of the applied voltage is required to circulate full load rated current. Again you remember that this is R net, this is J X net, this is usually the load, but this is short circuited, and this is the V1. This is the equivalent circuit, simple equivalent circuit of the transformer. So since the load impedance, this is the Z net of the transformer, and this load is not there, this is short circuited. So, to supply full load current, a very small voltage which is required. You remember we say voltage regulation should be around few percentage. So, if this is 5%, then 95% is expended here. That means, this impedance value is like 95:5, that is like about 19 times the leakage impedance or the net leakage impedance of the transformer. So, if you have to supply full load current only through the net leakage impedance of the transformer, you will require much less voltage. We have covered this aspect in detail in the previous lecture, just emphasizing it again, that this number 125 for the short circuit test is not at all surprising. You need a very small value of voltage to supply the full load current, and corresponding primary current is, full load primary current would be 15 amperes. Actually, it would be 15 plus whatever is the magnetizing or open circuit current. I am sorry, it will be I 2 dash plus open circuit current whatever is required, which is approximately which is equal to 15 amperes. And but if the magnetizing current here can be ignored, because the voltage developed when full rated current is flowing through 1/20th of the rated impedance, then you can say that the voltage developed across the terminals will be also 1/20th of the rated supply voltage. So, and V is equal to 4.44 f phi m n. So, if V is 1/20th of the rated value, phi m will be 1/20th of the rated value. If phi m is 1/20th of the rated value, then if this is the normal hysteresis curve, the hysteresis curve during this test will be such a small value. So, this area will be negligible, and similarly eddy current losses are also going to be less, because the voltages are going to be less, because the flux are going to be less, and the rate of change of frequency remaining the same. So, therefore, we can ignore open circuit losses and assign this 600 watts completely to the I square R, which is the copper losses, net I square R, the copper losses in the two windings put together. So, the 600 watts is therefore the PSC is the copper losses PSC, and if this is the and the no load current is also negligible, because the flux is much smaller. So, the no load current as it is only a few percent of the full load value, and now the flux developed is 1/20th of that. So, the no load current will be of, let us say 2% is the no load current, 1/20th of that will be like 0.1%. So, therefore, that can also be ignored. So, therefore, this is this number here is as good as the primary current, and the secondary current in this case will be almost like N 1 by N 2 by N 1, and so this is as good as the full load current on the primary. But anyway, this is I 1, this is V 1, and what is, if this is V 1 which I VSC which I have applied, this is the full load current which is flowing through it, and this is R 1 plus R 2 dash, and this is J times x 1 plus x 2 dash. Then if I calculate VSC by ISC in terms of magnitude, what will I get? I will basically get the impedance Z, I will just call it as leakage of the transformer, this mainly because it consists of leakage, that is why I am calling it as Z leakage of the transformer, or in other words VSC will be I 1 ZSC. You just take the product of the magnitudes and you will get this VSC. And if you look at the equivalent circuit, this is the V 1, this is the I 1, this current will lag by an angle phi S c, and this phi S c is basically R 1, I mean let me not call it R 1, it is R 1 plus R 2, let me just call it as R net, J x net, and this is the phi S c. So, therefore, I also know the lag from the short circuit test. I basically know everything about the impedance of the transformers, because I know this value which is the magnitude, and I know the angle, and therefore, I know all the parameters. But this problem does not require us to calculate the parameters of the transformer. It is directly asking us to calculate the efficiencies, the regulation, the performance of the transformer as seen by the end user. So, let us proceed with that. So, what is it? First, let us see what all we are asked to calculate. A, calculate the effective efficiencies at full load and half load at power factor at 0.8. So, the output is going to be S cos phi. So, it does not matter whether it is leading or lagging. So, 50 into 0.8 will be 40 kilowatts. 50 is the rating of the transformer in kVA, and the output after multiplying by cos phi will be in kilowatts. And what is going to be the input? The input is going to be output, which is 40 kilowatts plus losses, which are made up of copper losses and iron losses. So, the iron losses are 400 watts, they do not change at all, 400 watts. So, if I want to write it in kilowatts, either I should do everything in kilowatts or I should do everything in watts. So, I will do 400 as 0.4 kilowatts, and since the full load is prescribed, that means the load current is at its 100% value, the copper losses will be exactly as measured in the short circuit test, which is 600 watts, which will give you a value of 41 kilowatt. So, therefore, the efficiency is going to be equal to 40 by 41 into 100, which is going to be, this efficiency is going to be 97.56 percentage. So, this is my efficiency at full load. Now, let us look at efficiency at half load. Efficiency at, so output will now become 20 kilowatt, power factor remaining the same, and this becoming 25, this remaining 0.8, this will become 20 kilowatt. Now, the input power is 20 kilowatts, nothing happens to the, no change happens to the iron losses. So, it will remain at 0.4 kilowatt, 400 watts is 0.4 kilowatts, but at half the current, because the copper losses is proportional to square of the current. So, at half the current, this loss will become 1/4. So, therefore, this loss will become 600 into half square, which is 1/4. To convert it into kilowatt is to divide it by 1000. So, therefore, 125. So, 600 divided by 4 is 125 by 4 is 600 divided by 4, 150. 150 divided by 1000 is going to be 0.15. So, therefore, 20.55 kilowatts, 20.55 kilowatts. So, the efficiency now is going to be 20 divided by 20.55 into 100, which is equal to, a little deterioration has happened, 97.32 kilowatt. So, the copper, because the copper losses have come down, but the iron losses have not come down. So, therefore, we have got this little degradation in the efficiency of the transformer. Now, let us take the next set of problem, which is B, the voltage regulation for power factor 0.8 lagging and leading. So, as far as the efficiency of the transformer was concerned, lagging or leading did not make any difference. But now, when we come to the voltage regulation at a power factor of 0.8 lagging or leading, there is going to be some difference which is going to happen. We will see that. So, if you recall, I had given a simple derived in the last class a regulation on primary voltage base as what is it, V s c divided by cos of phi s c minus the load power factor divided by V 1 into 100. This is in percentage voltage regulation. So, we know that V s c is given to us. What is the V s c given? This is actually V s c, the primary applied voltage is 125 volt in the short circuit test. So, this is 125 into cos of, now there are two power factors that we have to look at. Let us first look at this one, where power factor is 0.8 lagging. So, if the power factor is 0.8 lagging, 0.8 lag, cos of phi is 0.8. So, phi is 36.86, and so this minus 36.86 is fixed. This is below is 3300, and of course, this 100 will remain as it is. Now, we just are left to calculate this phi s c value. So, what is the phi s c value? We know that short circuit loss divided by the volt amperes which is applied at the short circuit in the short circuit test, V s c into I 1 is 15 amperes, the full load current which is flowing. This is 125 volts and this was 600 watts. So, 600 watts divided by 125 into 15, just let me check my numbers, yeah, 125, 15, 600, I am right. So, this is, let us just calculate what is the phi s c. So, 600 divided by 125 divided by 15.32 and 0.32, let us look at the cos inverse of this. Let me write this as 0.32. So, phi s c is 71.33 degrees. So, let me subtract from this 36.86, 71.33 minus 36.86 is 34.47. I take a cosine of that, I get 0.8244, which I multiply by 125 and then divided by 3300 times 100. So, I get 3.122%. So, the regulation of the regulation of the transformer is 3.122%. So, what is our question? Voltage regulation for power factor of 0.8 lagging and second is 0.8 leading. So, when I am calculating for 0.8 leading, let me change the current color for 0.8 leading power factor. So, the phi will become now minus of 36.86 degrees, and so the percentage regulation is going to be equal to VSC into cos of phi SC minus phi L divided by V 1. So, 125 cos of 70, how much was that? 71.33 degrees, minus minus will become plus. So, 36.86 degrees divided by 3300 into 100, which is going to be equal to, let us calculate this. So, 71.33 plus 36.86, 108.19 degrees. So, cosine will be negative. So, cosine will be negative. So, therefore, their cosine will be negative. So, therefore, you are sure now that percentage regulation is going to be negative. So, that is first thing that we take. Cosine is minus 0.312 into 125 is this much divided by 33 is going to be minus 1.18%, 1.182%. So, therefore, now this thing is negative, right. I mean, so the percentage voltage regulation is negative, that means there is a voltage rise on the secondary side. And why is that happening? I mean, connected back to some part of the earlier times when I used to do compensation using capacitors to improve the voltage, and the capacitor basically gives you a leading power factor. So, what again this is showing is that if the load is having a leading power factor, then the voltage can rise on the load side with respect to the source side. This is important, this looks non-intuitive, but this is the way it is. That is why we have inductance as a device which tends to drop the voltage in general, and to compensate for it we use a leading power factor or capacitance to improve the voltage. So, the third part of the problem now is straightforward. Third part is C says secondary terminal voltage corresponding to 1 and 2. So, secondary terminal voltage V 2 is first of all the turns. So, secondary turns this what is the rated voltage at the secondary side? Let us start from there, 400 volts. So, the rated secondary voltage is 400 volts, then 1 minus the regulation value in per unit. So, in the first case the regulation value is going to be in per unit 0.03 122, which is approximately 400 into 0.97, 97% of the 400 volts will be available. That is around 388 volts will be available in the case of 0.8 power factor lag. Now, in case of 0.8 power factor lead, V 2 will be 400 into 1 minus the per unit voltage regulation, which is minus of 0.01182, which is approximately 400 into 1 plus 0.01, which is going to be 404 volts or so. Let us just check it. 1.01 into 400 is 404 volts. So, slight increase in the voltage of the transformer is happening. That is good, that is very good. So, we have solved one, we have seen how useful it is to have a to conduct this open circuit and short circuit test, because we can make calculations from these test data at different loading conditions, different power factors, different loading conditions. We can calculate efficiency, as well as we can find out what would be our secondary terminal voltage. So, without actually physically connecting it, we are able to predict or tell how the performance of the transformer will be. Now, let us move on to auto transformers. That is the next topic I am taking up, a very interesting topic, auto transformer. So, what is an auto transformer? An auto transformer is essentially a device in which the primary and the secondary windings are connected in series to boost the voltage on the secondary side. So, I have this single phase transformer, which I have now connected this is the V 1, this is the V 2. So, the V 1 and V 2 are in additive way here, connected in an additive way, the V 1 and V 2, and this is made the output of the transformer, and this is the input of the this is made the input of the transformer. In this particular case, the way I have wired it is in this particular way. The primary superimposed, connected on the stacked, in some sense, if you can say, I have stacked the secondary winding on the top of the primary by making a electrical connection like this. I have made a electrical connection like this, from this to this, and then this is where the primary is, and with respect to this ground, and this is where the secondary is, the V 1 plus V 2 is coming. So, let us see what is the output of such a connection. There is now one thing which you note in the auto transformer is a electrical connection has happened between the primary and the secondary. In the normal single phase transformer, there is only magnetic coupling between the primary and the secondary, but here there is a electrical connection between the primary and the secondary, and both magnetic and electrical coupling exist. Now, in this case, the output voltage is going to be V 1 plus V 2, and this current, this I 1 current flows here, I 1 current flows here. The MMF balance principle is still valid, because these two are magnetically coupled core, just like here they are same magnetically coupled cores, and if iron is taken to be ideal element, then N 1 minus N 2 I 2 should be 0. So, if this current is going to carry I 1 magnetizing MMF, a demagnetizing MMF I 2 has to flow out from this side, and therefore, I 1 plus I 2 has to come from the supply, and MMF balance is there, but the output voltage is no more V 2, but the output voltage is V 1 plus V 2. So, you see output voltage has increased from the single phase normal transformer operation, but the loading current is the same, output current is same as I 2, and so therefore, you can take V 2 I 2 out and write this as V 1 by V 2 plus 1, which is same as, if the rating of the transformer is S, then V 1 by V 2 is N 1 by N 2. So, you can see that the power rating or the voltage or the volt ampere rating output VA of the transformer or the voltage rating VA rating of auto transformer is increased by a fraction of it's increased by a scaling factor of 1 plus N 1 by N 2. So, you can get more kVAs, more MVAs out from the from a auto transformer paying the same cost. and at the same time, since the voltage ratings of primary and secondary are same. So, therefore, the flux levels are same. So, the core losses are going to be same, and the current in the primary and the secondary windings are again at full load operation, again at the same rated values. So, therefore, copper losses are also going to remain the same. So, therefore, if losses remaining the same and the output V A or output, if you take unity power factor, then this output V A is same as the kilowatts which is available or megawatts which is available at the output of the transformer. It has increased. So, therefore, efficiency of a auto transformer is more than the efficiency of the normal isolated single phase electrically isolated magnetically coupled single phase transformer. So, that is one important thing that we take note of this. Now, let us see if output has increased, we should also verify that the input V A also should increase. So, at the input side, you see the current becomes I 1 plus I 2, but the voltage remains V 1. So, here the current remained at the rated value, and there was a voltage amplification which was happening. At the input side, there is a current amplification that we are seeing, the voltage remains at the rated value. So, therefore, this can be again written as V 1 I 1 into 1 plus I 2 by I 1, but V 1 I 1 is the rated output of the transformer, single phase transformer. I 2 by I 1 is same as N 1 by N 2, and so we again see that the rating of the transformer has again increased by the same value 1 by N 1 plus N 2. So, this is the most important part of the transformer. Let me just brief you on some of these conclusions that I have got here. Rating of the auto transformer is bullet points. Rating of a auto transformer is 1 by 1 plus N 1 by N 2 times the single phase transformer. Cost saving of at a slight expense of improving the insulation level of the secondary winding. Why do I need to improve the insulation level of the secondary winding? Because here suppose this was 200 volts and this was 800 volts, then now this is at 1000 volts. So, the insulation level has to correspond not to 800 volts, but has to correspond to the 1000 volt rating value. So, slight expense of improving the insulation level of secondary winding, losses remain the same. So, efficiency of the auto transformer is much higher, lower leakage reactance, usually that is the way they are built, and only if I can say a small drawback it is there is the electrical coupling between the primary and the secondary, which is the cause of boost in the rating of the transformer. So, I feel always comfortable when I say that the primary and the secondary are only magnetically coupled, but there is no electrical coupling. So, if the magnetic coupling is weak, I will get less induced voltage. If the magnetic coupling is high, I will get a highly magnetic. But if there is a electrical coupling, then anyway whether the magnetic coupling is weak or high, whether the core is saturated or not saturated, if I by mistake touch it, I am going to get a shock. So, therefore, electrical coupling looks more dangerous than the magnetic coupling. When the core saturates, anyway the magnetic coupling comes down. That is the thing here additional, that you have a higher means the electrical coupling is more, but space is also saved. See, the larger rating transformers you make, single phase transformers you make, you need more iron, more copper, and they become bulky. So, many substations in the transmission system actually use auto transformers for their work. So, now let us solve one example of example with a auto transformer. A 1000 kVA, a 1000 kVA single phase, a 1000 kVA single phase transformer has a voltage rating of 800 volts. I just choose nice numbers, nothing about these numbers, just ease the calculation. Has a voltage rating of 800 volts and to 200 volts. So, V 1 is 800, this is 200. Can we reconnect it to serve a 1 kV load? Yes, we just saw that, right. I mean, stack this V 1, stack this with proper, this dot markings please note, I can also stack it to make it negative V 1 minus V 2, but that is not the idea at all to do. In the auto transformer, we are stacking it in such a way that V 1 plus V 2 becomes available at the output. This is I 1 plus I 2 and I 1 will flow here, I 2 will flow here, it is the same figure. So, can we reconnect it to serve as a reconnect it to serve as a 1 kV load? Yes, we can. If yes, how many kilovolt amperes can it deliver? So, if you connect it like this, you are going to deliver 1000 kVA into 1000 kVA into 1 plus N 1 by N 2. So, 800 by 200, which is equal to 5000 kVA. So, this is the output of auto transformer. Can you see 1000 kVA device is now delivering 500 kVA, it is almost like a magic. I did not do anything to really to the device, it is just the same device, it is the magic of interconnecting the primary and the secondary properly in series. That is why I like this device. Now, in this case it is very clear that this is the primary, this is the secondary, but in some sense you can always you can always say that designation of primary and secondary in a transformer is being a bidirectional device is arbitrary, convenience, whatever you can call it mathematically, you can call any winding as primary and any winding as secondary. So, therefore, if alternately, this is just for fun of it I am talking with you, if you had taken 200 volt as primary, that means you had stacked like this, this is the 200 volt and on this I had stacked the 800 volts and then connected it like this, 1000 volts I would have still got, then the output would be now 1000 into 1 plus 200 by 400, because the primary is which is only 1000 times 1.25, which is 1250 kV, still higher than 120, but now because I have reduced this I 1 plus I 2 remaining the same, now it is not multiplied by 800, but it is only multiplied by 200. So, therefore, what I am getting is that only 1250 kVA vis-a-vis 5000, but still higher than the 1000 volt amperes. So, this is the two possible outputs, but in this particular case it is clear this is primary, this is secondary and this is this. So, how many kVA can it deliver? Ideally, you should want it to deliver this particular value of kVA. So, now just to mention a few other things before I start with the I mean after some time I am going to start with the 3-phase transformer also, but before I go to 3-phase transformer, I also want to make a mention that the transformers transformers are also used for instrumentation purpose. In this way, in this they are called as instrument transformers, usually abbreviated as IT. Now, there are two types of instrumentation transformers, voltage transformer and a current transformer. So, we use transformer as a CT, this is called a CT, this is called a CVT. So, for example, I can have a transformer, the principle is the same, but the usage is different. So, if I have a CT, for example, a transmission line CT, then I will have that CT designated as 1000:5 CT. That means 1000 amperes is 1000 amperes should come as 5 amperes on the secondary, because instrumentation that you connect should not be will not be rated. Usually it would be some electronics and so on, or anything relay or whatever. It is not supposed to carry 1000 amperes. So, usually it looks like this. This is my transmission line and I have a CT is shown like this, and this may be like a very small burden here like 1 ohm or something. So, if this is carrying 1000 amperes here, 5 amperes will come out here, and so the voltage which is going to be developed is only very small value 5 volt, which usually you will connect it to analog to digital converter, sample it out, and from here measure the voltage being proportional to current. By calibration you will measure that the current is 1000 amperes. So, if the current is 500 amperes, you will measure 2.5 volts here, and therefore, you will effectively measure this. So, this is a symbol used for this is a symbol which is used for a current transformer. It is clear to you that the primary, the high current winding, the primary winding comes in series, and the instrumentation, this 1 ohm comes in load. So, this is the correction. So, the CT should have as limited impedance, as small impedance as possible, because it does not want to alter this transmission line impedance or whatever load which is connected to the transmission line. It does not want to alter the net impedance of it when you insert it for measurement purpose. So, ideally you should say that its impedance should be 0. So, here we will not say we want to make a CT with 10% leakage impedance. No, the leakage impedance has to be kept as small as possible. Also, the way this device is built could be somewhat different than the construction point of view. For example, say this is my transmission line which is there, then I would like have a core around it, a clamping kind of device or whatever you could think of it, and I would have the secondary winding. So, this is like as if a single turn primary, and here is the, so 1000 amperes, here is what is going to be the 5 amperes and then the 1 ohm. So, the constructional feature of a transformer of a CT could be much different from I am sorry, from a regular transformer. If you come to voltage transformer, usually it is going to measure like 400 kV transmission line. That means, line to ground or line to neutral is 400 by root 3 kV. So, it is going to step down this voltage to around 110 volt 3 phase, or single phase it is 110 by root 3 volts. These numbers have been standardized from past times when you used to have relays which were driven by these instrumentation transformers. If you today look at the electronic instrumentation that we have, these numbers could be even much lower. There is no harm in having these numbers at a much lower value, but since this has become a standard, this is the way it is kept. Now, if you look at this, this is just a normal single phase transformer, but turns ratio is extremely high, 400 by 110. I mean, this is two. If you just take this denominator as approximately equal to 100, then this is like 4,000 is to 1 turns ratio. Unnecessarily a very bulky device is being created just for the purpose of instrumentation, and the VA ratings of such instrument transformers is very low, because their job is only to do instrumentation. Their job is not actually to drive any large amount of power. For example, suppose this is 1 ohm resistor, then 25 into 1, which is the 25 watts, is the required volt ampere capacity of the transformer. So, VA capacity of the transformer is very small. Now, this to reduce the size of such a transformer, voltage transformer, what is usually done is a potential grading philosophy is used. So, you stack up series capacitors in microfarads in series, and then if this is V1, a small percentage voltage is V2 is available here when if you stack it at this point, and then you connect a normally instrument transformer here, normal step down transformer, and connect your burden or load. In instrument transformers definition, it is called a burden, because ideally they should not serve anything, they should just measure, but because we have they drives like 1 ohm resistor, there was driving 25 watts, it is the burden which is imposed on the transformer, and by doing this, this size of transformer is reduced much more smaller value from 4000 is to 1 turns ratio, and these are small and neat devices, capacitors, compact devices. So, a potential divider using the capacitor series stack is created, and this itself could be again a series parallel combination. It is not necessary that it should be only one, but for the sake of our description I have shown it like this, and then you get this as this thing. Performance of so this reduces this device is called CVT, CCVT or CVT, capacitance coupled voltage transformer. This size is much lower than a normal VT transformer. These devices are usually studied in more detail, their performance is much more studied in a protection course, where the protection systems meant to detect faults on the power system and isolate faulty equipments. They take their inputs, fault currents and voltages from this instrument transformer. So, their performance plays a critical role in critical role there in defining the performance of the protection system. So, these devices performance CT, VT, CT and CT or PT, as it is also CT. The first device is called as PT, voltage transformer. The basic voltage transformer is called as PT or a CVT or CCVT. They are discussed in much more detail in a protection course, and I am not therefore going to dive deep any further into that. With this, we will stop this lecture here today. Thank you.